For all of existence, we've been made to look up at the sun and the stars, and for as beautiful as they may seem, we'd wonder, what exactly are they made of? This is one of the many questions that I'm sure has haunted the minds of scientists for thousands of years. And frankly, answering this question has only been made possible in the last couple hundred of years through the use of spectroscopy. The two major types of spectroscopy being emission and absorption spectroscopy. The application of this spectroscopy would be to use the light emissions from celestial bodies in order to determine their molecular composition. So, just for a bit of a history lesson, this type of spectroscopy goes all the way back to Newton and his famous prism, which showed that the light from the sun could be transformed into a continuous spectrum of all lights of the rainbow. This idea was then further expanded on by Josef von Fraunhofer when he decided to take a spectrum of the entire sun's wavelengths pictured here. And what he noticed was that in the spectrum of the sun, that there were several dark spots. Now, this could not have been explained back then, for he didn't have the theoretical knowledge necessary. But Gustav Kirchhoff, several decades later, was able to figure out that these dark spots were the result of absorption done when molecules from the hot interior of the sun leave and interact with the cool exterior of the sun. Um, what this is referring to is the interaction of electrons in an atom, where in an excited state they absorb energy to go up to higher energy levels, pictured here. But when they go to the cooler surface of the sun, they are forced to relax and emit the absorbed energy in the form of photons that correspond to how much energy was absorbed. This is convenient because it means that both absorption and emission spectra give practically the same information, as the energy to move from one energy level to the other is always fixed. This then allows us to use to figure out which atoms are present, because each one would have a different and unique spectra due to their electron configurations. As seen here are some simplified emission spectra of the different elements. Um, and you can see how they're all unique to each other, and they're all different. It was because of this property that we were actually able to, fun fact, figure out that helium was on the sun before we were able to figure out that it was on Earth. And it is because of these bands of lights being unique that we could explain why there were dark spots in Fraunhofer's spectrum in the first place. Now, practically speaking, in order to get these emissions, we use satellites, such as the famous Hubble telescope, for an example, which have these built-in spectrographs and these mirrors, which are able to take in light from celestial bodies and translate them into spectra, which can be analyzed for their contents. Now, it's not only stars that we could find these spectra for. This is actually useful for determining the contents of atmospheres of other planets, for example, by looking at seeing which light from the sun gets absorbed by planets that are in the way of the satellite. Um, this is great for finding planets which may have similar compositions to Earth's atmosphere, consisting of carbon dioxide, water vapor, and methane. Now, going back, as we can see in this graph here, we have some more realistic spectra that you would expect from a telescope, and this was used to look at a lava planet to see what that was made of, and they were able to find out that there were such things like silicon oxide, magnesium, iron, and some oxygen. It is because of these innovations in spectroscopy that we've been able to get the privilege of knowing what these celestial bodies are made of, what planets are made of, and frankly, this gives us the tools to better explore the universe and better know what we're doing. Thank you very much.